Hi, this is Tom Radna, again for R for Lean Six Sigma, and the subject of this video will be the one-way ANOVA using R. And the assumption I'm going to make is that you know what a one-way ANOVA is, and we're going to go through an example with a set of data and how to do a one-way ANOVA within R. So the practical question that the data that we're going to look at refers to is around the etching rate or the speed of a plasma cutter at different power levels applied to the etching machine. So at different power levels, 150 watts, 200 watts, etc., does that have any impact on the etching rate? And we'll go through the approach in a practical, then graphical look, analytical look, and then back to the practical question. That'll be our approach in doing this. And we're going to take a look at the data in a stack format. We'll just take a quick look. We'll use a box plot and a bar chart with confidence interval error bars. We'll run the ANOVA model. We'll make conclusions. We'll also look at Tukey's test to determine which means are different, and then how do you check assumptions like about your residuals in your data set as well. Okay, so just at a high level, the ANOVA function is AOV, and what you pass to it is a representation of the model of your response variable as a function of your treatment variable, and use the tilde to represent the function of. R likes the data to be in a stacked format, so we will ensure that that's the case as we go forward with this example. So the vector we're going to be using is called etches, E-T-C-H-S. And we can see that there are two columns in our data. One's the etch rate. That's our response variable, continuous data. And then we've got power, which is the different levels of our factor. And we're just seeing the P1s as we are using the head function just to take a look at the variable from a high level here, the first few items in the data set. We can also take a look at the structure of our data frame etches. Again, we can see that rate and power are the two variables. Rate is an integer variable, power is a factor with 4 levels. And those are the 4 levels. The means of those 4 levels will be our experiment of interest here. So the first graphical approach we can look at is the box plot. And in earlier videos, I went through the details on running the box plot, but here again you can see that we're providing to box plot rate as a function of power, the data set's etches, and then some bells and whistles to pretty it up a little bit. And looking at our box plot, we can see that there looks to be some differences at each of the power levels. Of course, box plot gives us median, not mean, but as we'll see later, the data in at each level of the factor power is in fact normal. So the mean and the median will be approximately the same or very close. But we could also take a look using a function that I wrote that's not a base function in R, but it does give us that does give us the means as bars on a bar plot, along with error bars that indicate the 95% confidence interval of that mean. And again, from this graph, we have some inspiration that, in fact, these means at some of the levels could very well be different. So let's go ahead then and actually run the ANOVA model. And here again, we use the AOV function. Rate is a function of power. and the data set is etches, and we store that model that this function returns into another vector called etches_model, and then we can do a summary on that vector to give us our ANOVA table. And as you're likely familiar, we'll take a look at the p-value. And here we have a very, very small p-value, less than 0.001. And typically we're looking at a critical value for p of 0.05. And if p is low, we reject the null hypothesis, which in this case is that all the means of all the groups are equal. And we since we reject it, we go in favor of the alternate that says at least one of these means is different from the rest. And again, as I indicated earlier, the p-value is low, so we'll reject the null hypothesis. And that, again, the means of one of these levels is different than the rest, for sure. But the thing is, we don't know at this point which one or which ones are different from one another. Now, when we looked at the box plot, I said that the normality of the data at each of the subgroups, that in fact the data was normal in each. And here's how you can check that. There's the Innocent-Darling normality test, which is commonly used in other statistical packages. And as it turns out, that the Innocent-Darling normality test isn't included as part of the base packages that come with R, but it is in a package called NORTest. So you can install that package, and then you can use the ad.test, which is the normality test. Just note in R that it needs at least 7 data points to work. And if not, there is an alternate normality test you can use. Matter of fact, there's many normality tests, but the Shapiro-Wilk is one that comes with your normal package, with your normal R installation, and that can be used as well. And of course, when running a normality test, if the p-value is less than 0.05, then the data is not normally distributed. So I'm going to load the NORTest package with the library command, and then I'm going to test each of the 4 factor levels for normality of the data. And to do that, I've used the tapply function in R, which says run the Anderson-Darling test for the data etch rate at each level of the power etches. So you can certainly look for help on the tapply, but that's all really what it's doing. And that's really handy that it can, with a single command, check all 4 or how many ever levels of that factor power. And we can see at each level the p-value is much higher than 0.05. And as we can see, P1, P2, P3, P4. Therefore, the data is normally distributed at each level of the factor power. We should also check that there's equal variance in each of those subgroups. And we can do that with, in this case, the Bartlett test, because our data is in fact normally distributed. So we can run the Bartlett test of homogeneity of variances. And again, here we got a very large p-value. The null hypothesis for this test is that all the variances are equal, and the alternate would be at least one is different. And with the large value, we fail to reject the null hypothesis and can say that the variances, in fact, are equal at each level of power. In case you have a situation where the subgroups are not normal, you might be used to using a Levene test, but here there's also the Flinger-Killing test of homogeneity, and this is for non-normal data, much like the Levene test you might be used to running. Okay, we should also check our residuals. And we can do that by just plotting the model. And this will give us 4 plots of the residuals. The first 2 for me are of interest. And that is the fitted values versus the residuals. And we look for them to be equally distributed around the 0. As you recall, the residuals should have a mean of 0, be normally distributed, and have equal variances. And this plot gives us a sense that that's the case in this situation. And then we also get a normality plot. And it looks like we might have a little something going on here. But for the most part, most of the points are pretty close to the line that we would expect them to be. There's 2 more advanced plots that I don't typically look at. You can certainly dig into those on your own, but the first 2 are really the ones that are most handy for most Lean Six Sigma approaches. Now, what's also important is now that we know that at least one of the means is different, which means are in fact different, and we can do that by running a Tukey's test. And the command for that is Tukey HSD, and again we pass the ANOVA model that we created earlier. And what it does is a pairwise comparison of each of the means at each of the factor levels. And we can see each pair, in fact, is different from one another. The p-values are all less than 0.05. So in this case, it looks as though all the means are in fact different from one another. Now, I also like to utilize one other package and do a slightly different version of the Tukey test that does give the groupings, right? So I know which means I'll fall into the same group. And that comes out of a package called Agricol AE. And it is, again, from another, like I said, it's a different package. And it stands for Agriculture Analysis of Experimental Designs. And if you want more information or in the history of this, you can install the package and use the question mark to get the help. But I'm going to go ahead and load this library and then run the Tukey's test that comes with this library. And again here you can see the function we're going to run is hsd.test. We pass it the ANOVA model again. We have to tell it which factor that we're interested in seeing, and we need to tell it to send the results to the console by setting console equals true. And then I also collect the model that this creates in another variable called HSD. And it gives information on each of the levels and the means, the mins and max, but I'm most interested in is the grouping here. And what we see is that at each of the factor level, it's a different Tukey's group. So it's labeled A, B, C, D. If any of them were in the same group, they would share a letter. But means with different letters are significantly different from one another. So this is the nice output. We can also get a nice graph to represent this. Now we do have to set the max y value to ensure we can see everything we want. I'm going 1.2 times the size of the mean to leave some room at the top of the graph. And we'll go ahead and run it. It's bar.group. And then what we pass it is the groups variable onto the model we created from the HSD test. And again, I'm passing it values for the y. And over here we can see now that the means at each level are labeled with their letter group. And again, each of the means is different. So in fact, the etch rate is a different value at each power level, with P4, which is also the highest power level, giving the fastest etch rate. And we can see that P3, P2, P1, they all decrease. And that also relates to the size of the power level and that the rate goes down with each. So our final practical conclusion is that the highest power level is giving us the highest etch rate. And if that was something we were interested in, we would set the value there. So that wraps us up on a quick tour of ANOVA in R. If you find this of value, please feel free to leave me a comment, or again to reach out to me via Twitter or email. And the Twitter is R for LSS, and similarly the Gmail account is R for LSS @gmail.com. Thanks for listening.